In this video, I'll discuss using radios to transmit and receive data in a Campbell Scientific data acquisition system. I'll cover differences between spread spectrum and narrowband radios, antenna types, attenuation, signal strength. Narrowband radios transmit on a single frequency. In this demonstration, the yellow signal represents the signal traveling between two stations. The blue signal represents another signal at the same frequency. This overlapping signal prevents a clean signal from reaching the base station. Narrowband radios work best in remote installations where competing radio sources won't interfere with the signal. Spread spectrum radios use frequency hopping of direct sequence changes across a wider span of frequencies, typically in the 900 MHz or 2.4 GHz ranges. Because of this, a competing signal can only interfere with the system signal if it's at the same frequency. Higher or lower frequencies are not affected by the errant signal and reach the base station. Narrowband radios are better for long-distance links with a stronger reach, often have a longer range than an equivalent spread spectrum radio, are best for small periodic messages, are not ideal in areas with heavy radio traffic, are more vulnerable to interference from other signals on the same frequency, may require a license depending on band, power, and location, and are commonly used in point-to-point installations. Spread spectrum radios are best with clean line-of-sight links and in multi-site networks. Their range is often shorter than an equivalent narrowband radio. They can handle more data with higher throughput. Handles busy networks better, depending on the system. They are more resistant to interference as frequency hopping can dodge interference from other signals. There are often license-free options at low power, depending on the frequency used. They are commonly used in networked installations with multiple transmission sites. In summary, choose a narrowband radio when maximum distance is needed, when data is transmitted in occasional quick bursts, the connection is a simple A to B connection, and frequency coordination licensing can be managed. Choose spread spectrum radios when there are multiple sites with clear line of sight, higher throughput, frequent messaging is needed, improved interference avoidance is required, and a license-free radio option is desired. The purpose of using a radio link is to span distances that aren't practical with a cable. For example, sending data from a remote station on a ridgeline back to the base. To achieve a reliable link, I want the cleanest, strongest signal possible. Two key concepts to understand are antenna gain and the use of decibels, dB, to characterize the antenna gain. Antenna gain indicates how well an antenna focuses energy in a particular direction. The antenna isn't creating extra power, it's concentrating the signal where it's useful, either when transmitting or receiving a signal. Radio signals can vary widely, so decibels, dB, a logarithmic unit that expresses a ratio between two signals, often relative to a reference level, are used to report signal strength rather than stating an absolute value. Gains add and losses subtract. Overall, the goal is simple: reduce losses and keep the signal as strong as possible from one end of the link to the other. Radio manuals often include tables showing how specific decibel ranges correspond to signal quality levels for that particular radio. For example, a directional Yagi antenna aimed at the other side can pick up a stronger signal than an omnidirectional whip that listens equally in all directions. In this example, a directional Yagi antenna aimed at the signal source with 6 decibel gain can receive a stronger signal than an omnidirectional whip antenna with 0 decibel gain. In this section, I'll talk about ways to increase signal gains and reduce losses. Choosing the right antenna is a big part of increasing signal gain. Campbell Scientific radios are used with 3 antenna types. Dipole antennas consist of 2 elements in a straight line and are directional. A dipole transmits and receives most strongly perpendicular to the antenna elements. Performance is best when antenna orientation and polarization match the incoming signal. A dipole antenna can provide up to about 2 decibels of gain. Yagi antennas are also directional. They use one driven element, a reflector behind it, and one or more directors in front to focus energy in one direction. When transmitting, aim the Yagi toward the receiving site. When receiving, aim it toward the transmitter. A Yagi will typically provide about 8 to 12 decibels of gain. Omnidirectional antennas transmit and receive in a full circle around the antenna, with a coverage pattern that is roughly donut-shaped. Signal strength above and below the antenna axis is significantly lower. Omnidirectional antennas typically add 2 to 9 decibels gain. Next, I'll look at how signal loss can occur through attenuation. Attenuation is the reduction in signal strength as a radio signal travels over distance or through a medium. Signals become weaker due to absorption, scattering, resistance, or simple spreading. Common contributors to attenuation include antenna cable losses. Resistance in coaxial cable reduces signal strength and loss increases with cable length. Poor or loose connectors can also introduce significant loss. Radio frequency. Higher radio frequencies typically experience greater attenuation. Distance. As the signal travels away from the transmitter, it spreads out and weakens, reducing the signal level at the receiver. Atmospheric absorption. Water vapor, rain, fog, smoke, and snow can increase signal loss. Obstructions in line of sight. Obstructions can block or partially absorb the signal. Some materials like glass may allow some signal through. Others may block it almost completely. Multipath fading, Fresnel effects. Signals can reflect off hard surfaces and arrive at the receiver via multiple paths. When those paths arrive out of phase, they can reduce the overall signal strength received. Notably, water may act as a reflective surface. All these factors combine to determine the final signal level at the receiver. With an understanding of what affects radio signal strength, the best placement for the transmitter, receiver, and antennas can be planned. Key best practices include: locate a position that gives direct line of sight. Avoid signal paths that pass through trees or heavy vegetation. If possible, avoid installing radios and antennas near large, flat, reflective surfaces that could increase multipath reflections. Mount the antenna as high as possible without interfering with any sensors, and use the shortest cable possible to connect the antenna to the radio. Once locations are selected, choose transmitter and receiver antennas that will provide dependable communication for the specific link. In the United States, Campbell Scientific offers a radio test kit that can be used to evaluate different radio and antenna combinations in the field. The kit includes a base radio and a test radio, multiple radio options, and a collection of antenna types available from Campbell Scientific. By adjusting parameters and trying different antenna configurations, the test kit helps identify the best combination for a specific site. Contact Campbell Scientific to learn about renting the radio test kit. Choosing the right radios and antennas doesn't have to be difficult. With a little preparation such as scouting installation sites, planning for line of sight, and testing configurations when needed, a reliable radio network can be built to transmit collected data back to the base station for retrieval. For more information, visit our website or contact a Campbell Scientific representative with questions about radios, antennas, and deployment best practices.